Good day, everyone. So, what we're going to talk about today is trigonometric identities. Specifically, we're going to go into reciprocal identities, Pythagorean identities, as well as sum and difference. So, since we are just now getting started into Chapter 7, something to keep in mind. We're going to be doing a lot less applications of trigonometry and more of the identities, more of the proving type material. So the material that we learned back in Chapter 6, like as opposed to like the unit circle, radians, things like that, we're not going to use it too terribly much in this chapter. But what we will use is your basic fundamental knowledge of trigonometric functions, such as your knowledge of sine, cosine, and tangent, secant, cosecant, and cotangent. So in this chapter, one thing I really need to hit on the most is that you will have to use a lot of definitions and a lot of, identities, okay? So I highly recommend, highly recommend getting a flashcard, a note paper, something like that, because you're going to have to write down a lot of these identities and kind of keep them in memory, because you're going to be utilizing them. You're going to be using these tools to solve problems. So specifically, the first set of identities we've got to be familiar with are called even and odd identities. Now, even and odd identities actually go back to what we learned in algebra with regards to even and odd functions. Of course, you can always go back and review, but even and odd functions, remember they were symmetrical with the y-axis, symmetrical with the x-axis, symmetrical with the origin, stuff like that. So it actually plays the same role in trigonometry. So some even functions, even trigonometric functions, sine of a negative angle is equal to the negative sine of that positive angle. Cosecant of that negative angle is equal to negative cosecant of the positive angle. Tangent of negative your angle equals negative tangent of your positive angle. Cotangent of your negative angle equals negative cotangent of your positive angle. Okay? So these are the even functions that we want to be familiar with, because anytime we have sine of, let's say, a negative 30 degrees, that's the same thing as negative sine of positive 30 degrees. And of course, we can utilize our special triangles to figure that out. But in order for us to figure it out, we've got to use these even functions to rewrite it in ways that we are familiar with. That's really the whole point of this chapter, is rewriting problems in such a way that we are familiar with how to work them. Odd functions, cosine of your negative angle is equal to positive cosine of your positive angle. So basically, if you're taking the cosine of a negative angle, automatically that's going to turn positive. And it's because they're odd functions. And then secant of your negative angle is equal to positive secant of your positive angle. Okay? So those are even and odd functions. We're going to be utilizing those quite a bit throughout the entirety of this chapter. Not just this section, but this chapter. This section over here is talking about reciprocal identities. Now, reciprocal identities play on some knowledge that you should be familiar with back in Chapter 6. Remember what you know about sine, cosine, and tangent, secant, cosecant, and cotangent. Remember the old saying, if you have not heard this before, okay? Socatello. Some old hippie caught another hippie tripping on acid. All right? So that's how a lot of folks remember the basic trig functions. Reciprocal identities means that if you flip those values, you get the other trig functions, the secant, cosecant, and cotangent ones. Specifically, sine of your angle is equivalent to 1 over cosecant of your angle, because sine and cosecant are reciprocals of one another. Cosine and secant, cosine is equal to 1 over secant, because cosine and secant are reciprocals. Same goes for tangent. Tangent of your angle is equal to 1 over cotangent. Tangent and cotangent are reciprocals of one another. Same pattern goes for cosecant and sine, secant and cosine, cotangent and tangent. Basically, these are kind of flip-flopped with one another. Now, some other ones that we are definitely going to have to be familiar with are these guys over here. Now, these are reciprocal identities, but they're written in forms that we should be familiar with, if not, are going to be familiar with. Because tangent is equal to opposite over adjacent when you're dealing with your triangles. The opposite side is generally going to be your vertical. If you're measuring your angle from the origin, your vertical is always your sine because it dealt with y over x, or I'm sorry, y over hypotenuse, so y. Your cosine was always your adjacent, your x. Okay, so that was x over your hypotenuse when you dealt with the triangles. So tangent is also equivalent to the sine of your angle over your cosine of your angle. Okay, that's another way to write tangent. Same goes for cotangent. Cotangent is also equal to cosine over sine. All right, so those are some functions, some identities we've got to be familiar with. We're going to utilize pretty much the majority of these identities in these problems, especially with the ones you're going to see in my math lab. Now, these little guys down here, I did kind of run out of room, so that's why I kind of put it down here. Pythagorean identities. These identities come from the unit circle, specifically the unit circle. Basically, the first Pythagorean identity, and this is one that everyone should be familiar with after they finish trigonometry. Cosine squared plus sine squared should equal 1. Okay? That is the foundation of the unit circle. If you're ever curious about the theory behind it, let me know. I would be more than happy to describe it to you. I might put you to sleep, but I promise you there is a long and drawn out theory behind it. The second Pythagorean identity is 1 plus cotangent squared theta equals cosecant squared theta. The third one, definitely an important one, 1 plus tangent squared theta equals secant squared theta. All right? So, I'm going to give y'all a little bit of chance to write these down, and then we're going to start solving some problems using these identities. Alright, so we're going to start off relatively simple when it comes to solving identities. Okay? As always with videos and with online classes, you can always hit pause if I'm going a little too fast, and then just after you're done trying to catch up on it, just hit play again. So that is no problem at all. So the first problem we got, the directions are going to be pretty straightforward. Usually they're going to just say simplify. All right. So the first one, sine of beta, where beta is your angle, minus tangent of beta, okay, and then times sine beta plus tangent of beta. Okay? So the reason why the directions say just simplify and nothing too elaborate is because when you're simplifying identities, you're trying to get it down to as lowest terms as you can. Okay? And when you get it as low as you can, if you try to do some fancy stuff to it, then you're going to overcomplicate it, and really it's going to be like beating a dead horse. Okay? There's no really other way I can describe that. So how do you know when you're done? Well, you know when you're done whenever you got it looking very pretty, it's very short, it's concise, and if you do anything else to it, it's going to make it look more complicated. Okay? Which means you're working backwards. We don't want to do that. So for this problem here, we're going to bring it back to algebra. This is where college algebra really comes into play. Because we have two parentheses that are being multiplied together, guess what? We get to FOIL. Remember your first, outer, inner, last method. Okay, so your first, outer, inner, and last. Alright? So when we FOIL these guys out, what we get is sine times sine, which would be sine squared beta. Right. Except that marker is no good anymore. So we get sine squared beta. Okay. Sine times tangent of beta. Let me elaborate. Sine times a positive tangent of beta is positive sine beta tan beta. Okay. Remember, we did the first terms together. Now we did the outer terms together. Now we get to do the inner terms together. So a negative tangent of beta times sine of beta. Okay, so if you want to follow that pattern, it'll be negative tan beta sine beta. Okay, they're being multiplied together. But if we keep them like how we have right here, because multiplication is commutative, which means the order and how you multiply it does not matter, we can actually write this as a negative sine beta tan beta. And I'll show you why I did that in a little bit. Okay? Actually, it'll be in not this step, but the next one right afterwards. And then if we multiply the last terms together, negative tan beta times positive tan beta is a negative tan squared beta. All right, so what we did here, we FOILed. Okay, so basically what I'm going to start doing, I'm going to have the word here, and then I'm going to actually write out what we did in English. Okay, that way when you're going back and reviewing the videos, you're able to see, oh, well, that's what he did. He FOILed it. Or he combined like terms or something like that. All right, so now we got to here. And it looks a lot more complicated than what we started off with. But here's the cool part. Remember back when you did FOILing, some stuff canceled out. Some stuff was able to be combined into simpler terms, aka combining like terms. The reason why I wrote it like this originally, okay, like the sine beta tan beta right here, is because a positive sine tan beta minus sine tan beta. These are like terms. They're the same thing. So a positive and a minus, well, guess what? They cancel each other out. Okay, so these guys literally just go to zero. So all we have left is sine squared beta minus tan squared beta. And what we did was just combine like terms. Okay, and that would be our final answer. All right. So that is how we're able to even do a basic solving of a trigonometric identity. All right. Now, as always, you can go back and review this video just to make sure that you're able to comprehend and follow along. Okay. Now, on this one, we didn't use any of the identities that we did or that we had written down. The reason why is because I want to show you guys, even since we're doing trig, we're still using a lot of algebra behind this. Okay? So just something to keep in mind. All the stuff that we learned back in college algebra, it does not go away. It's still going to be there, y'all. All right? So let's take a look at another problem. Now this one will use the identities that we had written down. All right? So this one is, same direction, simplify. Cosine x sine x times cosecant of x plus secant of x. So now take a look at this, see what y'all come up with, and try and catch up to y'all, okay? Now, a little trick that I learned along the way when I was trying to solve identities, right, is you want to get your identities or your final answers in terms of sines and cosines. That's really what you want to boil it down to. Once you get it in just sines and cosines for your answer, that's how you know you're done. All right? So, just kind of a little heads up. When you don't know when you're done, do you have only sines and cosines in your answer? If you do, more than likely you will not have to go any further. If you don't, kind of double check your answers, because most of the time when you simplify and reduce identities, they can be reduced into terms of sines and cosines. All right. So on this one, let's multiply cosine x, sine x, and basically we're going to distribute this into this parentheses. All right. So how that would occur, cosine x times sine x times cosecant of x. Okay? Plus cosine x times sine x times secant of x. Okay? Here we distribute it. Alright. Now, where in the world can we go from here? Well, darn. Can't really simplify it. They're not like terms. But, hang on just a second. We know some reciprocal identities. Specifically, we can rewrite cosecant of x and secant of x. When we rewrite those guys, something magical is going to happen right afterwards. So, going back to that a couple of minutes ago when I had all the identities written up, the reciprocal identity for cosecant of x is 1 over sine x. So this would be rewritten as cosine of x times sine of x times 1 over sine of x. All right? And then plus cosine of x times sine of x. And the reciprocal identity of secant is 1 over cosine. Alright, so basically what we did, we used reciprocal identities. Alright, now here's a magical thing. Stuff is going to cancel out. It's going to reduce. Specifically, this sine x here cancels out with this sine x. So all you're left with is cosine x times 1, or just cosine x. So these guys cancel out. And you're left with cosine x plus this cosine x cancels out with this cosine x here. So that goes away. And all you're left with is sine x times 1, or just sine x. So here, we reduced. And since our answer is only cosines and sines, that would be your final answer. Alright? So here, we utilize the tool of reciprocal identities to simplify our problem. Okay? But first, we used algebra, we distributed, then we were able to simplify our problem using the reciprocal identities, canceled out the stuff on top with the stuff on bottom, and then all we have left with is cosine x plus sine of x. There we go. All right, let's try another one here. I'm going to get a little bit more complicated. All right. Now, as the problems get a little bit more complicated, I may need to utilize this space over here, so I may not be able to write the steps that we do just because some of these problems may get a little bit long. But that's okay. All right, so let's take a look at this one here. This one is, well, same directions, simplify. Cosine squared x times sine of x divided by sine squared x times cosine x. All right. Excuse me. Apologize. All right. So hit pause real quick. Let's see what y'all come up with. There's a little teeny tiny trick on this problem, but you're only going to see that trick at the very end. All right. So for this problem here, there's not much you can do on the trig side. Okay, it's all going to be algebra really. So basically what we're going to look at, let's expand this out so we can look at each individual term. Okay, we can look at everything that we got. So cosine squared x, well that's really the same thing as cosine x times cosine x, and then we have the sine x tagged along with it. So cosine x times cosine x is actually cosine squared x. It's just cosine times itself. It's really all it is. And then the same process on the bottom. Sine x times sine x times cosine x with the little tag along. Okay, so we expanded this. Okay. Now, going back to the algebra, what can we cancel out? What can we reduce? Well, let's see here. A cosine x on the top can reduce with this cosine x on the bottom. This sine x on the top can reduce with this sine x on the bottom. All right. So what we got left is a cosine x over sine x. Okay, so here we reduced. All right, now, if the directions on this question asked you to leave it in terms of sine and cosine, that's what you would leave it there as, okay? That would be your stopping point because you can't really reduce it anymore using sines and cosines. But if they asked you to simplify as much as you can using identities, this is where you would use an identity. Cosine x over sine of x is equal to cotangent of x. All right, remember it was one of those little identities we have over far right over here. So cosine over sine, that gets us cotangent of x. All right, well, of course we use something, but that's a reciprocal identity. All right, so really, if the problem just said simplify, either one of these answers would work. But if the directions were very specific on what they wanted, in terms of sine and cosine, that would be it. Simplify using identities, cotangent of x would be your answer. So you got to be very careful on what those directions tell you. All right. So far, the bulk of what we've been doing in these problems has really just been algebra. It's kind of weird. All right. So let's see here. Let's see if I got a good one here. Ooh, yeah, this is going to be a good one. All right. This one here is going to utilize a lot of material that we learned back in algebra. It's even going to be a challenging one for me, too. Because I have not seen this problem in a long time. And all I have is just the problem. Okay? I don't have the actual steps written out. Which is good, because it challenges me, too, just as much as you guys. So this problem, of course, it would say simplify. Alright. So simplify the square root of cosine x on top over sine to the, that's a tongue twister. Sine of x to the 21st power. So sine to the 21st power of x. Okay? Basically, to translate that, it's sine of x times itself 21 times. Ooh. Yeah, tough one, huh? Now, this is where some funky math is going to occur. But I'm going to take it back to basics for you. I'm going to try. If you remember way back when in a galaxy far, far away, yes, I use a lot of Star Wars references. If you multiply something by 1, it's still that same something. So like 3 times 1, that's just going to be 3, right? All right, that's the last thing I remember. Okay, at least the last time I checked. 4 times 1 is going to be 4. Now, also too, if you take something and divide it by that same something, that's going to be 1. Excuse me. So like 5 divided by 5, that's 1. What we're doing is that we're going to use both of these processes to manipulate this problem behind me. Okay? So what we got, we're going to kind of rework this problem a little bit. And then, see, I'm not going to make it too complicated. I'm going to try not to. So, the reason why we're going to do this is because later on, we've got to deal with that square root right there. Excuse me. And right now, we can't do anything with the square root. That's what kind of bugs us. So, what we're going to do, we're going to utilize those 2 properties that we just talked about. All right. You utilize those 2 properties. Remember, if you multiply something by 1, it's that same something, so nothing changes. If you divide something by that same something, it's going to be 1. Okay? This is why we're going to do this. We're going to take the stuff on the inside here, and we're going to multiply it by cosine x over cosine x. Remember, this divided by this is the same thing, is 1. 1 times this is that same something. So these guys are, like this statement right here is still equivalent to this. It's still the same thing as that. So basically what we're doing, we're multiplying the radicand by cosine x over cosine x. Why are we doing this? Because this next step here, when we multiply straight across, then we get cosine squared x on top over cosine x times sine to the 21st power of x. All right. Now, why did that just happen? Why did we do that? Well, if you go back to your properties of radicals from college algebra, okay, that's why I'm telling you this right now. When you take the square root of a fraction, it's the same thing as the square root of the top over the square root of the bottom. All right. So I'm going to draw some arrows just so you can follow the process. So the square root of this whole fraction right here is the same thing as the square root of the top stuff divided by the square root of the bottom stuff. All right. Whew. Use a lot of algebra on this one. Now, specifically, when we broke up the square root of this fraction, that's what we call the quotient rule of radicals. All right? So square root of the top over the square root of the bottom. Now, when we work with each little square root separately, the square root of cosine squared, the square root of a square cancel out. They are inverses of one another, aka the square root on the top goes away. And you're left with cosine x on top over the square root of cosine x sine to the 21st power of x on bottom. Okay? So we still got that big square root on the bottom. So now the fun is going to occur on the bottom. How can we go about this? Well, going back to algebra, we can actually break up this stuff inside here. Specifically, that's sine to the 21st power of x. Okay? We can rewrite that, and the reason why we're going to rewrite that is because we're going to use fractional powers of radicals. Fractional powers, fractional exponents, however you want to say it. All right? Now, we still have the cosine x on top. Okay, that ain't changing. On the bottom, we now have cosine, and actually let me kind of clean this up real quick. Because it's being multiplied, I'm able to do this because the order does not matter. Sine to the 20th power of x times cosine of x times sine x. Now, what in the world did I just do? Oh my goodness. Sine to the 21st power of x is, like we said earlier, sine times itself 21 times. All I did on this step is I just took one of the signs out. All right, so that's why I have a sine to the 20th power. And then I have the sine x over here. So if I wanted to combine the two, I've got a sine 20 sine x's here, and I have a sine x here, so that would be 21 sine x's. Okay? Exponents! Fun stuff. Now, why in the world did I just do that? Because if we remember the fractional powers, fractional exponents, a square root is the same thing as a 1/2 power. Why does that matter? Because we get to use this 1/2 power on the sine to the 20th power of x. Now the cosine x and sine x, we actually get to leave those alone because we can't really simplify those any further. Okay, so we have a cosine x on top still over, all right, let me kind of backtrack real quick. If you have the square root of a product, just like we have the square root of a fraction, square root of a product is the same thing as the square root of the first guy times the square root of the second guy times the square root of the third guy. Just like the square root of the fraction. Square root of the fraction is square root of the top divided by the square root of the bottom. Basically, we get to break up the square root. So that would be the square root of sine to the 20th x times the square root of cosine x sine x. Now, I could have written the square root of cosine x times the square root of sine x. But it wouldn't have done me any good because I can't do anything with the cosine x sine of x. Okay, so that would have still, that would have been like being a dead horse. Okay, so that's going to be there. I don't need to do anything else with that. But that's where I'm going to start having some fun. So the square root of sine to the 20th of x, right? Because we said that the square root is equal to the 1/2 power, this would be technically sine of x to the 20th power raised to the 1/2 power. All right? That's technically how it's written. But to save some confusion, we can keep it like this as long as we perform this process. Right? That 1/2 gets applied to this 20. So what is 1/2 of 20? Well, 20 divided by 2 gives us 10. So cosine x on top over sine to the 10th power of x times the square root of cosine x sine x. Whew, goodness gracious. And guess what? That's all we can actually do. Because we can't really simplify the square root of cosine x sine x because we don't have any squares in there. Can't do anything else at the top. We're not doing any square roots of anything with this guy right here, the sine to the 10th power of x. So that's actually as far as we can go. You probably could break up sine to the 10th power of x and simplify a cosine, but oh my goodness gracious, it's giving me a headache just thinking about it. So this guy right here would actually be your final answer. All right. Now, the reason why I wanted to do this problem in particular is because a lot of the material that we're going to cover in trigonometry has a lot of algebra behind it. When that day comes and you guys take calculus at a university, whether it be LSU, whether it be LSUE, whether it be UL or SLCC, whoever, in calculus, we focus more on the calculus than we do the algebra because we expect you to know the algebra. But when you come in for tutoring or when you struggle in your assignments, we actually assist students more in algebra than we do in calculus. Like they're taking calculus and we focus more on the algebra when we're trying to help them because there's a lot of algebra behind it. Same goes for trigonometry. There's a lot of algebra behind trigonometry. So as you're learning the trig, you're having to refresh on the algebra. That's why I wanted to do this problem because there's a lot of material that you learned way back when that we gotta pull back. All right, there's a lot. All right. Now, these next formulas right here, these next set of formulas are what we call sum and difference formulas. Right? All right. So these formulas, these identities, excuse me, there are 6 of these guys. All right, so first one is cosine A plus B I kind of write these out a little differently, so bear with me. Minus. All right. Okay. So that's the first two. The second two excuse me. Sine, cosine. Cosine, sine. Alright, and don't worry, I'm going to talk through these, so don't worry. If you can't read them, it's all good. Tan A. Alright. Yes, these are the sum and difference formulas, and I will be honest, I don't have them committed to memory. Alright? Because that's why I strongly encourage writing them on a piece of paper, index card, something like that, because I do want you guys to use these formulas, actually use these notes or these index cards on your exams. Okay? There's just too many identities for one person to remember. The trick, the real important part, is how to utilize the formulas. That's the most important part about these guys. So there are 6 sum and difference identities. Cosine of two angles added together, A plus B, equals cosine of your first angle times cosine of your second minus sine of your first times sine of your second angle. Cosine of two angles subtracted from one another is cosine of your first times cosine of your second plus sine of your second times sine of your first. Sine of your first times sine of your second. Okay. Sine of two angles added together is sine of your first times cosine of your second plus cosine of your first times the sine of your second. Very easy to get mixed up in there. And then sine of your two angles subtracted is sine of your first angle times cosine of your second minus cosine of your first times sine of your second. Now tangent is where it gets a little funky. Tangent of your two angles added together is tangent of your first plus tangent of your second divided by 1 minus tangent of your first times tangent of your second. And then tangent of the two angles subtracted is tangent of your first minus tangent of your second over 1 plus tangent of your first times tangent of your second. All right? So definitely a decent amount of formulas. All right? Now the whole point of it, all right, is this. What if we're trying to figure out the exact value of an angle, but we're having to do it by hand, and we have to do it exact, and we basically have to use what we know? how in the world do we do that? Well, going back to chapter 6, we know 30, 60, 90 triangles, 45, 45, 90 triangles. Excuse me. And we also know the unit circle formulas or the unit circle angles. Anything in between there, that's where it gets a little tricky. That's where these formulas come into play. All right? So hit pause real quick. Write them down because we are going to use these heavily. You've got to know these formulas in order to do some of these problems. You got to. All right? I'm not asking you to memorize it. I'm just asking you to have it written down so that way when you're looking at the problem, you can refer back to that tool. All right. Now, what if we had a problem such as simplify the following trigonometric equation or trigonometric value. Tangent of 75 degrees. Okay? Tangent of 75. Well, if you go back to the unit circle, we do not have a 75 degrees listed on our unit circle. All right? If you do, you've got a funky unit circle. But we've got two angles on the unit circle that can add to 75 degrees. What do you think they are? 30 and 45. Haha! We're doing the adding part of tangents. All right? So, the formula we're going to use is tangent of 30 degrees plus 45 degrees. Okay? So that would be the tangent of your two angles add together on top over 1 minus tangent of your first angle times tangent of your second angle. All right, let's actually write this out. So, it would be tangent of 30, all right, plus, hopefully we can assume it's going to be degrees, tangent of 45 degrees over 1 minus tangent of 30 times tangent of 45. All right, so that is a sum and difference formula that we utilize. Okay? All right. Now, let me hang on just a half a second. Just thought about something. I'm still here. I'm trying to reference something just for half a second. My brain just went blank. This happens a lot. Yeah, my brain just went blank for half a second. Okay, there we go. Okay, so basically, the tangent of 30 degrees, obviously you can use a calculator for that, but I had the unit circle. So the tangent, I'm going to do a little scratch work. The tangent of 30 degrees is opposite over adjacent, which means it's 1/2 over square root of 3 over 2. Okay? This is actually how I'm so used to doing it because I can do sines and cosines, tangents, and got a little bit of work to it. So when I divide fractions, I keep, change, flip. Okay, so let's see, 2 square root of 3. Alright, so 2's cancel out, so I'm left with 1 over the square root of 3, which, if I rationalize, square root of 3 over 3. Alright? So, the tangent of 30 degrees is just square root of 3 over 3. Alright, so yeah, like I said, I had to do a little bit of scratch work. And that's okay. Plus the tangent of 45 degrees. Well, the tangent of 45 degrees better be 1. Okay. Over 1 minus tan 30, which is square root of 3 over 3, times tan 45, which is 1. All right. So now we did all the trig. Now we get to do some algebra. Square root of 3 over 3 plus 1, we're having to add fractions. Common denominator would be 3. So that means on the top, it would be square root of 3 plus 3 over 3, just on the top. And then on the bottom, we would have 1 minus the square root of 3 over 3. Okay? Which, on the bottom, it's a least common denominator of 3. So that means it would be 3 minus the square root of 3 on the bottom, divided by 3. All right? So, we have a fraction divided by a fraction. Keep, change to multiplication, flip. So the process is going to be, I keep the top fraction the same. I change my big bar to multiplication, and I flip my second fraction. All right? So I cancel out, and all I have left with is the square root of 3 plus 3 on top over 3 minus square root of 3 on the bottom. And that would be my final answer. All right. So let me kind of backtrack here. All right. Okay. So, excuse me. So yeah, utilizing your unit circle definitely comes in handy. Okay, I got to refer back to it all the time, so it's no big deal. So let's backtrack. Let's summarize. Tan 30 is the square root of 3 over 3. Okay, that's the exact value. Tan 45 is 1. So that means on the bottom we've got 1 minus tan 30, which is square root of 3 over 3. Tan 45, which is 1. So basically from here to here, we did the trick. Now from here on out is a bunch of algebra. So we got to add two fractions, or we got to add things with fractions, so we got to find the common denominator. So LCD would be 3 on the top. So that's why it would be square root of 3 plus 3 all over 3. On the bottom, we would have 1 minus the square root of 3 over 3. So that means LCD on the bottom would be 3. So 3 over 3 minus square root of 3 over 3. On the bottom, it would be 3 minus the square root of 3 over 3. Lots of 3 going on. Okay? Lots of fractions. And then to go from here to here, since we're dividing fractions, we keep, change, flip. Multiply by the reciprocal. That's another way to say it. Keep the first guy the same. Change your division to multiplication. And flip your second fraction. And then we cancel out the 3's here. Okay? Because these guys here are not the same. They are different. But these are the same. So we cancel out these 3's. And all we're left with is square root of 3 plus 3 over 3 minus the square root of 3. And that would be our final answer. So really the hardest part of this problem is the algebra, not even the trig. All right. All right, so let's look at another one here. All right. Sine of pi over 12. Now, I wanted to do this one in particular simply because sometimes we are going to have to deal with radian values, radian measurements, which means generally you're going to be dealing with fractions. All right. So, utilize a sum or difference formula using sine and see what you come up with. Now you have to think about this. All right. Sine of pi over 12. What two numbers will add or subtract to a 1 pi over 12? All right, we got to think about this. Now, 1 pi over 12. You can't have two numbers that add to a 1 because if you do, you're going to be decimal numbers, you're going to be in the negatives, you're going to have, that's going to be a whole mess. So we got to have numbers that would subtract to a 1 pi over 12. All right, so what numbers are you familiar with in the unit circle that would subtract to a 1 pi over 12? Well, the ones that come to my mind are 4 pi over 12 and 3 pi over 12. Well, it's because 4 minus 3 gets you a 1. That's what comes to my head. So, in other words, sine of pi over 12 would be the same thing as sine of 4 pi over 12 minus 3 pi over 12. Well, 4 pi minus 3 pi gets you 1 pi. And everybody likes just 1 pi, right? Nothing? Okay. So, to simplify that, 4 pi over 12 and 3 pi over 12, we really don't have those in our unit circle. But if we simplify it, then actually we do. So 4 pi over 12, 4 goes into 12 how many times? 3. So that means 4 pi over 12 can be reduced to pi over 3. That's something we're familiar with in the unit circle, as well as the special triangle. 3 pi over 12 can be reduced because 3 goes into 12 how many times? 4 times. So that means this would be a pi over 4. There we go. These are some formulas that we are familiar with. These are some angles that we see all day long in the unit circle. Now, we've got a subtraction of, with signs and everything. So the formula that we would use would be the difference formula using sine. Okay? All right, so this would be sine of pi over 3 minus pi over 4 equals sine of your first angle, so that would be sine of pi over 3 times cosine of your second angle, cosine pi over 4, minus cosine of your first angle times sine of your second angle. Okay, we're going straight off of the formula. That's all we're doing right here. Okay? Once we determine that it is going to be a subtraction, then we just follow that formula right down to the T. And then really, all this stuff here on the left side does not even matter. The meat and potatoes is happening right here. So if we go back to our unit circle and we determine what the sine of pi over 3 is, well, the sine of pi over 3 is going to be the square root of 3 over 2. The cosine of pi over 4 should be square root of 2 over 2. And then minus cosine of pi over 3, that should be cosine of 60 degrees, which should be 1/2. Okay. And then the sine of pi over 4, well, that's a sine of 45 degrees, square root of 2 over 2. So now we get to do some algebra. All right, we get to do some multiplication. The square root of 3 times the square root of 2 would give us the square root of 6 divided by 4. Because 2 times 2. Remember, when we multiply fractions, we multiply straight across. And then minus 1 times the square root of 2 is the square root of 2. 2 times 2 would be 4. So now our final answer, and if you put the square root of 6 minus the square root of 2, which is the square root of 4, you are wrong every single time because that defies the laws of radicals. Trust me, you would be surprised at how many times I see that. Because the square root of 6 minus the square root of 2 would be, if you were to go with that, would be the square root of 4, which reduces down to 2. If you put those in your calculator, 2 is not going to be the same thing as that decimal number that it gives you. Okay? So the square root of 6 minus the square root of 2, you cannot combine them, so they would be the square root of 6 minus the square root of 2 over 4. They would share the same denominator because they have, well, the same denominator already. So that would be your final answer. Okay? Now, like I said, you generally will have to deal with fractions when you're dealing with radian measurements. All right, so just keep that in mind. All right. So the last one I wanted to do, all right, is kind of working backwards. All right? And this typically throws students for a loop, and I love doing that because, you know, life will throw you curveballs here and there. Life does that. Trust me. Does it to me all the time. But I enjoy it. But what if you're having to work backwards? What if you've got to figure out what the actual angle is? Meaning, what if you're given sine of 27 degrees times the cosine of 42 degrees plus the cosine of 42 times the sine of 27. Okay? What if you're given that and you got to figure out what the angle is? Well, here you've got to figure out what formula to use. If you go back to your list of formulas, what formula matched sine of an angle times cosine plus, that's your key right here, that plus sign. Cosine of your second angle times sine of your first. Which one matched that? Actually, I had this backwards. My bad. All right. That was my mistake. So, but really, that plus sign should be the key right there. Sine of your first times cosine of your second times cosine plus cosine of your first times the sine of your second. That right there would be a sign of addition. Okay? So, that would be the sine of these two angles added together. All right. So that goes back to the formula. So basically what we're doing, we're given all the right side stuff, we just need to figure out the left side stuff. Okay? So in other words, once we determine this, all we have to do is add 27 to 42. Which means that would give us the sine of 69 degrees. And that would be our final answer. That would be the angle, the single angle that we are looking for to simplify this expression. Okay? Now, if you wanted to work it backwards, then yeah, you could figure out two angles that would add up to 69 degrees, which in this case would be 27 to 42. All right? That's all you would need to do on that one. Now, this concludes 7.1 material. Okay? Now, we are going to spend quite a bit of time in this chapter, but just keep practicing these problems. Yes, they can be a pain in the rear. I fully understand that. I truly understand that. But let me know when you guys get stuck. Notice how I said when, because everyone does get stuck on these problems one way or the other. Trust me, it happens. I'm always happy to help. I'm more than happy to write lecture videos and notes and things like that. But let me know what you guys are struggling with, okay? In the meantime, keep practicing, keep working hard, and I will start making up the videos for 7.2 on up, and then we will go from there. As always, let me know if you have any questions of any kind. See you guys next time, all right?